One quarry blast can knock loose 25,000 tons of raw stone, the weight of 2 Eiffel Towers coming down in seconds. Getting that mountain out of the ground is the easy part. Turning limestone into road base, cement, and eventually concrete is where the real engineering begins. Keep watching for the twist where farmers turn out to be quiet, steady buyers of quarry rock. Not a working quarry. That turquoise water at the bottom? Groundwater slowly filling the quarry. And every one of those neat terraces you just saw exists because of what happens next. Once a week, drill crews punch 15 to 30 holes into the rock face and set off a controlled blast that shakes loose up to 25,000 tons of raw stone in one shot. 25,000 tons. Roughly the weight of 2 Eiffel Towers coming down in seconds. Excavators load the debris. Haul trucks feed it to the crusher. Some of this rock will end up under a highway. Some will end up burned. Some will end up holding a building above the ground. One mountain, 3 completely different careers ahead. Before limestone becomes anything, it has to shrink. A crushing plant runs 500 tons of rock per hour through a chain of jaws, cones, and vibrating screens. Every stage cuts the stone smaller and sorts it by size. The rock that leaves here is already sorted into different futures. And the first machine that touches those blast piles has to swallow rocks. A primary sizer built for a limestone quarry in France chews through material rated at 152 megapascals of compressive strength at 1,000 tons per hour. 1,000 tons an hour. Man, that's a full tractor trailer load every 20 seconds. 2 toothed shafts turn slowly, tearing rather than pounding. The clever move is bringing the crusher to the rock instead of hauling the rock to the crusher. A fully mobile sizer rolls right up to the excavator at the working face, taking material straight from the bucket and putting it onto a conveyor at rates that can exceed 10,000 tons per hour. That cuts the diesel bill for haul trucks and pulls a whole fleet of pickups off the pit floor. Fewer trucks, fewer near misses on hairpin ramps, fewer flat tires the size of a hot tub. If you've watched a haul truck tire get changed, you know why nobody wants more of those than necessary. The same twin shaft principle also works hundreds of feet below the surface, in operations where hauling material up an incline costs more than the material itself. This footage comes from an underground mine, but the mechanism, low-profile design, and slow-turning teeth are exactly what a modern limestone sizer relies on. Once the primary sizer has done its rough work, the smaller stuff needs a different tool. A compact jaw crusher takes fist-sized rock and squeezes it between 2 steel plates until it snaps. Simple mechanics, blunt force, and remarkably little fuss for what it does. Now the material meets the machine that decides how uniform the final product will be. A cone crusher hides a steel cone spinning eccentrically inside a fixed bowl. The gap between them shrinks and opens hundreds of times per minute, catching rock, squeezing it, then releasing the fragments downward through progressively tighter spaces. The result is stone that comes out remarkably close to a target size. Over and over, all shift. Cone crushers are where aggregate stops being random rubble and becomes a graded product. If you've operated a crushing circuit for a season or two, drop a comment. What does the manufacturer's spec sheet leave out about real throughput? And this is where the paths split, because size alone starts deciding what the rock becomes next. Here is the first fork in the road, and most people never notice it exists. Not every ton of crushed limestone ends up in a kiln. A huge share of it goes straight into pavement, exactly as it comes out of the crusher, sorted by size and nothing more. Under any highway sits a stack of graded aggregate layers. Coarse stone at the bottom spreads the load. Finer stone above locks the layers together. Only the top few centimeters are asphalt or concrete, the shiny part your tires actually touch. Paving crews chase temperature all night long. Asphalt that cools too much before the roller passes will never compact right, and every stopped paver leaves a small dip a driver will feel at 70 miles per hour a decade later. The pavement is not the road. The pavement is a thin coat on top of a mountain that has been sorted, layered, and pressed into place. On a full highway rebuild, the numbers stop being cute. A portable ready-mix plant sits on site, feeding a continuous concrete paving train that lays a fresh slab lane by lane while traffic keeps moving in the other direction. Every truckload of crushed limestone underneath makes the surface possible. Night paving on an interstate is when the whole operation shows what it can really do. A rubber-tracked placer receives concrete from dump trucks and feeds it to a slit-form paver. The paver tracks over freshly placed material and extrudes a finished slab. A third machine follows, texturing the surface and spraying curing compound before the concrete has time to think. But some limestone never goes anywhere near a road. It has a completely different appointment. Back at the quarry, the question changes. For pavement, all that matters is how big the pieces are. For lime and cement, chemistry runs the show, and only certain deposits pass the test. Geologists study the reserves before a hole gets drilled, mapping which zones carry high enough calcium carbonate purity. Blasting patterns are designed to match the plant's appetite. From the pit face to the kiln, every step is measured, sampled, and adjusted. A limestone deposit that looks identical to the untrained eye can be worth 10 times more, or worthless, depending on what a lab report says about it. And this is where the rock stops being rock. Pre-crushed limestone gets dumped into a charging hopper, screened once more to reject, undersize, then fed by bucket elevator up to a vertical shaft kiln. Fuel and combustion air blow in from the sides. The stone travels downward, meets rising heat, and undergoes calcination somewhere around 900 degrees Celsius. Carbon dioxide leaves. What comes out the bottom is quicklime. Chemically, completely different from what went in, even though it still looks like a pale lump of stone. The lumps get pre-crushed to about 10 millimeters, then either shipped as is or ground in a roller mill into pulverized lime, moved by pneumatic conveying into silos, and finally loaded into bulk trucks. A rock walked into a chimney, and a chemical walked out. Whole transformation happens in one long fall. Not all lime ends up in construction. Some of it ends up in soil. Agricultural lime, or ag lime, is finely ground, calcium-rich limestone used to correct acidic farmland. Sour soil starves crops because plants can't pull nutrients out of it efficiently, and one spread of ag lime can lift yields for years. Farmers buying limestone by the truckload. Roman legions were moving this stuff 2,000 years ago. The quarry side of the operation looks familiar. Drilling, blasting, loading, crushing, screening. But the finished product skips the kiln entirely. Instead of being burned, the stone is ground fine enough that farmers can spread it across fields with a specialized truck. Most people picture quarries as construction suppliers only. Do you think farmers or contractors buy more limestone tonnage in the US each year? Share your thoughts below. The same quarry that feeds a paving crew can also feed a wheat farmer 3 counties over. Same rock, completely different customer. Step back to a full lime operation and you see something closer to a chemical refinery than a mine. Multiple kiln types run in parallel. Long rotary kilns with preheaters, annular kilns, parallel flow, regenerative shaft kilns. Each tuned for a different product grade. Downstream, milled lime, hydrated lime, and milk of lime peel off as 3 separate product streams. Every batch is sampled, tested, and tracked. Rail, road, river, and deep water shipping all leave the same plant because lime is heavy, and moving it far by truck alone would kill the margin. The last stop before the product leaves the plant is the one nobody films: hydration and packing. Once quicklime drops out of the kiln, it goes into a hammer mill to be sized down, then into a series of mixers where water is added under controlled temperature and pressure. That reaction is violent. Quicklime plus water releases so much heat that adding too much water too fast will boil it right out of the mixer. 6 minutes of residence time inside the hydrator, monitored step by step, is what turns quicklime into calcium hydroxide. From there, a rotary bagger with 10 filling nozzles packs up to 2,200 sacks per hour. That works out to a bag every 1.6 seconds, all shift long, and every one weighed automatically before it moves. And then the biggest change of all happens inside a rotating tube of fire. Here is where the mountain stops being a mountain. Limestone gets blended with clay, silica, and a pinch of iron, then fed into a preheater tower before entering a rotary kiln running around 1,450 degrees Celsius. 1450 degrees is about 10 times hotter than your kitchen oven on its worst day, and nobody inside is checking on a roast. At that heat, calcium carbonate falls apart. Carbon dioxide escapes. What comes out the other end is a hard, glassy pellet called clinker, dark gray, almost metallic, and nothing like the pale rock that went in. Clinker cools on a grate, then gets ground with a small amount of gypsum inside enormous ball mills and vertical roller mills. Only now does the powder deserve the word cement. Lab crews test every batch, curing test cubes in water baths for weeks to prove the mix meets strength targets before a bag ever ships. Follow the rock from the pit, and you can watch chemistry happen in slow motion. Blasting opens the limestone face. Haul trucks feed the primary crusher. Conveyors run the material into pre-blend beds where it gets stacked in long parallel layers, then reclaimed sideways so the raw feed stays chemically consistent even when the quarry's own chemistry drifts. Cement plants live and die on that consistency. One bad batch of raw feed and thousands of tons of clinker come out useless, so the lab checks samples every few minutes and adjusts the mix on the fly. The homogenized meal climbs a preheater tower 5 or 6 stages tall, dropping through cyclones that recycle waste heat rising from the kiln below. By the time the meal reaches the burner zone, it is already glowing before the flame ever touches it. Inside the kiln, a slow rotation and gravity do the rest. One integrated site can show every stage of this transformation in a few kilometers of pipe and belt. Drilling rigs prep the face. A controlled blast drops the wall. Loaders feed haul trucks that dump into a primary crusher. Conveyors carry the sized material into kilns where calcination happens under intense heat. A laboratory samples the product continuously, running automated analysis before anything leaves the plant. Finished lime and clinker load onto trucks and rail cars for shipping. And then a curious thing happens on a construction site. The powder from that kiln meets the crushed stone from the quarry, and they turn into something neither one can be alone. For the mat pour under a 40-story tower in downtown Houston, crews place 25,000 square feet of concrete in one continuous operation. 4 batch plants, 6 pump trucks, 136 mixer trucks, and 2 shifts of finishers ran for 13 hours and 16 minutes without stopping. Stop that pour halfway, and the seam becomes a permanent structural weak point. Say you're the site superintendent on hour 11 and a batch plant goes down. Do you slow the pour or push the remaining plants past their rated output? Tell me. Here's where a lot of people get the vocabulary wrong. Cement is the binder, the powder that came out of the kiln. Concrete is the finished mix, and cement only makes up about 10 to 15% of it. The rest is aggregate, crushed stone and sand, plus water and, on serious jobs, admixtures. And the smallest ingredient in the bucket often does the loudest work. Admixtures are liquid chemicals dosed in tiny amounts, sometimes less than 1%, but they control setting time, workability, and long-term durability. Step back to the whole built environment, and you will find aggregate hiding in plain sight. Roads, bridges, foundations, tunnels, runways, and ports consume huge volumes of crushed stone and sand. About 90% of concrete is aggregate. Here is what feeding that appetite actually looks like on the ground. A working aggregate quarry runs a chain of loaders, crushers, screeners, and conveyors from sunrise to sundown, sorting rock into a handful of product piles. Each pile has a target market. One bin for concrete producers, one for asphalt plants, one for road-based contractors, one for drainage stone. The same excavator can dig rock destined for a Costco parking lot in the morning and a hospital foundation in the afternoon. At peak, a mid-sized quarry loads 400 dump trucks a day. That is a truck rolling off the scale every 90 seconds through a full shift. And when demand climbs, the plant has to grow with it. A 2022 rebuild of a Pennsylvania quarry replaced the entire aggregate processing line. 2 new crushers, scalp screens, finish screens, wash screens, and conveyors. In the first 10 months, production doubled to 1.3 million tons. But making the stone is only half the work. Now you have to move a mountain out of the pit. Before the loadout can run steady, somebody has to solve the storage puzzle. A working quarry never produces at the exact rate the trains show up to collect. The plant runs continuous. The The trains come in bursts. Between them sits the stockpile, a buffer that keeps both sides from stalling. Track-mounted mobile conveyors line up in sequence, moving material away from the plant and building long, tall piles that the loader can eat from later. If you've ever tried to keep a Costco checkout line moving during a rush, you already understand the entire problem. Copper mines run these same systems at 800 tons per hour without a truck in sight. And the fancier stockpiles do a trick that saves quarries a fortune. They pile material without ruining it. A radial telescopic conveyor can extend, retract, and swing in an arc, autonomously placing rock in layered concentric piles up to 1,000 tons per hour. Coarse rocks roll to the outside, fines settle to the middle. When a loader digs into that pile later, it scoops a completely different blend depending on where the bucket hit. Smart stockpiling keeps the blend uniform from the first bucket to the last. Add a dust containment hood, spray bar suppression, galvanized covers, and PLC-driven condition monitoring, and the machine essentially runs itself all shift. Look closer, and the loadout is a small chemistry problem disguised as a conveyor. Wash and screening stages pull dust and fines out before the material reaches the loading tower, because contaminated aggregate arriving at a customer's plant means a rejected train load and a very tense phone call. At a working quarry, every train starts with the boring part, getting rock from a pile into a hopper car. Dump trucks tip aggregate into a feed chute, a conveyor lifts it up and over the tracks, and gravity drops it neatly into the cars below. Once the crushers hit their stride, the loading yard becomes the choke point of the entire operation. A Texas quarry runs 14 miles of private track, a 9-mile loop, and an automated loadout system that pushes up to 400 fully loaded trains out every year. But there is a scale even this doesn't touch, the kind that shows up floating. And when the market wants aggregate in bulk shipping quantities, everything on land has to keep up. A self-discharging vessel can unload 2,500 tons of crushed stone every hour into a radial stockpiling conveyor at a port. That is a full dump truck emptying every 25 seconds, all day. Follow one piece of crushed limestone all the way through the network and you see how far a rock really travels. Hopper cars loaded in a Pennsylvania quarry roll across state lines to a depot in Delaware. Smaller aggregate unloads by gravity through hopper bottoms onto a belt. Larger stone gets picked out by a straddle carrier excavator walking above the gondolas. A depot like this is where the industrial chain finally meets the local market. Dump trucks roll in, load a few tons at a time, and drive out to the next parking lot, driveway, or bridge deck. One mountain, 3 completely different careers. Part of it is crushed and graded, then buried under the road you drove on today. Part of it climbed a preheater tower, lost its own chemistry inside a kiln, and came back as cement powder. And then those two paths met again inside a truck, mixed with sand, water, and a splash of chemistry, and poured as concrete under the building above your head. Cement production accounts for roughly 7 to 8% of global CO2 emissions, and growing construction keeps demand high. Some engineers are pushing cleaner kiln fuels and carbon capture. Others argue that recycled crushed concrete could replace a significant share of virgin aggregate before we solve the kiln problem. Which lever moves the needle faster? Cleaner kilns or reusing what we already poured? Weigh in below. Appreciate you watching all the way through. Tap subscribe. The next deep dive is already loading. See you. Take care.